Hey guys, welcome back to my YouTube channel. Today we're going to be talking about four things. We're going to be talking about the Big Bang, the Higgs field, fundamental particles, and fundamental forces. And we're talking about how they relate to each other in a sort of big picture format. So after the Big Bang, there was a lot of energy released from it, quote unquote, and there was a lot of electrons and quarks. So there wasn't actually atoms as we are familiar with them today that are put together and it's really nice and neat. Instead, you had what atoms are made of. And there are three mechanisms by which the building blocks of atoms came together to build atoms, and it's three things: the Higgs mechanism, nuclear binding energy, and potential energy. So start with potential energy. Everything in the universe is constantly seeking a state of lower potential energy for the most part. It's the same reason, and it does so through taking the path of least action. And it's just the same reason as if you put a ball on top of a hill and you kind of give it a little shove, it will naturally go down the hill because there's a lower state of potential energy at the bottom of the hill as compared to the top. And so the same applies with the atom. So the potential energy of whenever you put everything together, all the different parts together of the atom as a whole, is less than the sum of the potential energies of the building blocks. So it's basically energetically favorable. Second thing I want to talk about is nuclear binding energy. Nuclear binding energy is a really fancy word for the amount of energy associated with it being put together. That is how much energy is needed to be used to be put together. And you also have something called a mass defect, which is when the atom does come together. If you measure the amount of mass before and then after it comes together to form the atom, there's actually a little less mass after it came together. And it's believed that that little amount of mass, again, the idea is mass defect, was converted into nuclear binding energy, the energy required to put it together. And then lastly, we have the Higgs mechanism. The Higgs mechanism is the process by which all matter gains its mass. And the idea of it is that you have this thing called a Higgs field. Higgs field is a really special term. Um, it's not a part of space-time, but it does exist within it. And the idea is that it exists everywhere in every single cubic centimeter of everything, and it assigns a value to each point. And the idea is that whenever particles move through the Higgs field, if they have the associated charge with the Higgs field, what will end up happening is that it will cause a disturbance within the field, also called an excitation. And this excitation produces Higgs boson particles, and along with those Higgs boson particles, it starts to slow down as it's moving through the Higgs field, and it gains its mass. And the strength of its interaction with the Higgs field determines how much mass it has, or in other words, how slow it starts to move through the Higgs field. Without the Higgs mechanism and via the Higgs field and the Higgs boson, everything would move at the speed of light because everything would be massless, just like photons. You see in this little picture right here, the idea of the picture is that photons, unlike quarks and electrons, are massless, and they do move at the speed of light because they cannot work with the Higgs field because they do not possess the associated charge with it. So the bottom left corner, it looks a little weird, the image, but there's an analogy that came up to describe this. And the analogy is that imagine you have like a party full of a bunch of people, there's a crowd, there's a lot of people, and you take two people. Each person starts at one end of the crowd and tries to walk across the crowd. And one person is, say, for example, Brad Pitt or Ryan Reynolds or some other super famous person. And what ends up happening is because of how famous they are, as soon as they start trying to get across the crowd, people start to crowd him and get around him and start to talk to him and all that nonsense. And so the more amount of people that start to surround him, the slower he moves through the crowd. And you take another person who's not so famous, they try to walk through the crowd. The opposite happens. Not many people start to talk to him, so he can move through it more easily. And so that's the idea with the Higgs field. Again, the idea of the Higgs field is that it gives elementary particles, such as electrons and quarks, their mass through the interaction with it. And here I want to talk about all the elementary particles. These are all the elementary particles. I'm going to start with all the ones, only the ones that I want to focus on with this is going to be the up, down, electron, gluon, photon, and Higgs. So let's start with up and down. Up and down is what makes up a lot of our ordinary matter. And by ordinary matter, I mean specifically protons and neutrons, these two things. Again, protons and neutrons make up the nuclei of every single atom. The proton is positively charged and the neutron is neutrally charged. And the reason why the neutron is And the reason for this is because, as you can see, the U and the D represent up and down, and the up quark, as you can see here, has a plus 2/3 charge, and the down has a negative 1/3 charge. So for neutron, if you have 1 up, therefore plus 2/3, and then 2 down, which is the negative 1/3 together, is minus 2/3. Do the math and you get 0. And the proton, since there's 2 up and 1 down, do the math and you get an overall net positive charge. And so the idea of these other quarks, these charm, top, strange, and bottom, they're really mysterious, but the idea is that they're a result of when 2 of these elementary particles, these quarks, kind of collide together in really high speeds. And they basically, what happens is that you get these. That's the idea of it. And they're heavier, and because of that, they're more unstable, and they're more likely, or they will start to like degrade, break down, and release its individual parts. And that's where you get all these other things like these down here. Whenever these heavier quarks sort of are created, they are unstable, so they break down, they produce these things. There's really 2 main ways in which this happens. They can happen in nature through cosmic rays, something that naturally happens, or they can happen with a man-made machine called a particle accelerator, which just does exactly that. It forces them together. The gluon again, or excuse me, the Higgs field, the Higgs boson, this right here is, again, has to do with the Higgs field. It's the excitation of the Higgs field caused by the movement of a particle, and they work together in unison to give that thing its mass. For the mathematics that we've done for it, we actually aren't 100% sure that what we think the Higgs boson is actually it. It's just a close estimation, so we think so. Gluon has to do with the gluon is also associated with the proton and the neutron and these up and down quarks. The idea is that the gluon actually works to keep all these things together, so it kind of binds them together. And the photon, so a photon, again, like we said before, we're going to talk a little bit more about it in a second, but the photon is massless. It moves at the speed of light in a vacuum, and then through like but if it's not in a vacuum, its speed will be slightly less. I think that's good. So this next slide has a lot of stuff. So we're going to start with the top left corner. Top left corner, as you see everything breaks down into smaller parts. Everything is made of something else until you get to a point where there's nothing else. So if you see, it starts with matter. All matter is made of molecules, and molecules are made of atoms, and atoms are made of the atomic nuclei or nucleus and electrons, and then the atomic nucleus is further made of protons and neutrons, and then the protons and neutrons are made of, again, like we said before, quarks. And then what we see actually here, though, is strings. And string theory is a sort of new theory. It's and it's also sort of not proven. It's not solidified. It doesn't have a sufficient amount of evidence to sort of make it official. But it is a pretty good theory. The idea of the string theory is a candidate for the theory of everything. So let's talk about this a little bit. So within theoretical physics, you have 3 main big ideas, which is special relativity, gravity, and quantum mechanics. And the idea is that these 3 big main models, specifically these 2, though, explain a lot of stuff. They work really well, and they're used in physics to describe a lot of what happens naturally. But the problem is that they sometimes don't. There are some scenarios where if you do the math and you do the experiments, you will find that they just don't work. They start to almost explode, and they don't work well with each other. And really, it's just like the physics of big things, or like macroscopic things, isn't the same as the physics of small things, like quantum things, like quantum mechanics. And so they don't work well together. The math isn't mathing. You have problems with black holes, which is that the center of the black hole has a infinite density, which really doesn't actually make sense. It doesn't exist. There's no such thing as infinite density. It might work well with mathematics, but with physics, it doesn't work. A black hole having an infinite density in the center is just a way of saying that we really don't know why that seems to be that way, or sort of what it means, though we do have some ideas about it. So let's go back to string theory. So string theory is a possible candidate for unifying all these 3 things together by basically providing more information as to fill the gaps, to say this is wrong here and this is the new part that we're going to add. And what string theory is specifically is It's the idea that everything is made of strings if you go down further enough, and strings aren't made of anything else. The idea, if you look at an electron, it seems to be a point particle for the most part. It does exhibit particle wave-like duality. But when you think of it in terms as a point particle, you see it as like a dot. And the idea is that if we were able to get a higher resolution and zoom in more, what you'd actually see is it's actually a string, this like circular thing. And the idea is that everything is made of strings, and all strings are identical except for the way in which they vibrate. And so if you have a string that vibrates one way, you get that is a particle, like X particle. And then if it vibrates another way, it's a different particle. And so yeah, the problem with it, there's two main problems with it. One is that string theory, if you do the math, it can only work in a universe with 10 dimensions. Ours is 4. We have three spatial, 1 temporal. And so one of the things they're doing two things to solve that problem, which is that they're trying to do the math and work backwards into how many dimensions we have, which is 4 again. Or they're trying to say that maybe we really are in a 10-dimensional universe, and it's just that these other dimensions are so intrinsically and uniquely folded onto each other that we actually just don't notice it. The other problem with it is it's so small that you just can't see it. And if you can't see something, or you can't really experiment with it, that creates further problems. So let's talk more about these three ideas. We're going to talk about in the next slide quantum mechanics, or a few slides from now. And let's talk about relativity. So special relativity and general relativity are two very similar ideas, or they're two similar models proposed by Albert Einstein. Special became first, and then general came second. General introduced gravity into a model. But let's talk about what it means. Let's talk about it in terms of space-time. So the idea of relativity is that space and time are not two separate things. Rather, they are one unified thing. So you can't think of space without thinking of it as also being something related to time, and then vice versa. It also says that, so when you think of space, there's like up and down, right and left. Those are the three, and then one time. And so the sort of analogy that has been come up to explain this is the analogy of a flip book, which is that, I'm sure you're familiar with it. A flip book has all these different pictures, and it's almost like the same image, but as you're flipping through it, the picture moves. And so you'll have to imagine that is kind of like what space-time is. Another major idea of relativity is the name. So why is it called relativity? It's called relativity because space and time are both relative. You can't think of time as being this thing where there's this absolute, objective, universal time or universal clock that everything beats around. Instead, time and space can only be thought of in terms of how it's relative to the observer. And so there's two things related to that. One is gravity, and two is speed. The faster you go, if you go near the speed of light, this causes you experience space different, and it actually causes you to experience space. It's like space kind of like gets shorter. And so there's an experiment, like a machine that's been created, where you've got protons basically being accelerated around a ring, like a circle, within a machine, and it's going so fast. It's not going the speed of light because it theoretically can't, but it's going very, very near the speed of light. And they did the math, and it's about like so many kilometers or something like that. And they did the math, and what they found is that even despite the distance they're actually traveling, from our perspective, is like 3 kilometers. It's actually, if you do the math, they're actually traveling 3 meters because they're experiencing space different relative to the particle. So that's one example. The other example is time, which is that there's no universal clock. You can't say, and the reason for this has to do with gravity, which gravity is something that comes into play with general relativity. General relativity says that gravity is a curvature in space-time, and that it's not so much as a force as it is just a curvature or a disturbance in space-time, and it creates these hills and valleys. And the idea is that so here's the image. The idea is if you have like a big piece of like rubber and you put a bowling ball in the middle of it, what happens? The bowling ball sort of sinks into it, and it creates this shape. And if you put another object near it, it will naturally, because of the distortion of the rubber, it will come down near towards the bowling ball. And so that's the same idea there. So I guess we could say Einstein and Isaac Newton sort of disagreed on that idea. And so the other thing about it, though, is one, again, gravity is a fundamental force, part of the three other ones. Gravity is actually a very, 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 very weak force relative to the size that the object is, which is why you only see stuff like planets and stars and black holes, these really big things, actually being able to exhibit, like you can see and feel and experience the gravity. Technically, everything does have gravity in the sense that everything has mass, therefore it supports space-time, so therefore has some level of gravity around it or drawn to it from other objects, but it's just that the planets are big enough that the small extent of gravity can actually be experienced. But the other thing is that if you distort space-time enough, therefore you have enough gravity, you will actually experience time differently. And I guess an example of this is that a clock beats slower here than on the moon, and it'll beat even slower compared to here than on the sun. The idea is that the more mass something has, the more gravity it has, and the more gravity it will have as a result of it, and the more gravity there is, the slower time beats for that thing. So that's why it's called relativity. It's relative. Everything's relative to each other. There's also another problem. So you get a lot of problems with these two things. Again, you get mathematical errors such as infinity errors or divide by zero errors when it comes to black holes. And there's also another problem having to do with quantum entanglement, which is the rough idea is that you got two particles, and or two wave-particle duality particles, and their waves sort of coincide. They start to work together, and then you could just separate them from a very long distance. And whenever you measure one, something about it, that causes a change in the other, despite no matter how long the distance is between them. And so the problem with that is it seems to suggest that however a mechanism by which they're communicating with each other or affecting each other can be fast in the speed of light, because you can put as long of a distance between them. But according to relativity, according to Einstein, you can't go faster than the speed of light. There's also another problem, which is that, say, if there's a bus and there's a fly in the bus. Say the bus is going X miles per hour and the fly is flying forward. You would say, according to Newton, you would say that the fly's velocity is actually the velocity it's going plus the velocity of the bus. But say, for example, you have a rocket ship going very, very near the speed of 99.9, and you have the same fly or something moving within it, and you were to add the velocities, it would suggest that it could go faster than the speed of light. But the sort of solution to this is that, again, when you're going near the speed of light, there's the space that it's moving. The space gets distorted, the space kind of becomes shorter, and so you have to add that into your calculations, and that's why you can't move faster than the speed of light if you have a fly on a rocket ship. Let's look at these fundamental forces of nature. So these are the four fundamental forces of nature. We talked about gravity. So strong interaction or weak interaction, these are actually more commonly called a strong force and weak force. I don't know why they're called an interaction here. The idea of the strong force and the weak force really simply is that the strong force has to do with nuclear binding energy, the energy that has to do with the force involved with keeping the atomic nuclei together. That's why it's called strong, because you have to have a lot of force to do that. Otherwise, it's just going to fall apart. And the weak force has to do with sort of doing the opposite of that, which is taking parts away from it. And of course, it's weaker because it's being destroyed, not put together. And then electromagnetism. We're talking about that more in a little second. The rough idea of electromagnetism is that, of course, everything's made of protons and electrons, and the protons have positive charge, the electrons have a negative charge, and they're really just like tiny magnets. Kind of like if you take two magnets and you try to get the north end and north end, push it together, it repels, and if you put the north and south, it attracts. Same idea there. The proton and protons will repel each other, electrons will repel each other, and the protons and electrons will attract each other. And that's part of the reason why the atom has the shape it has and everything is where it is because there's something about the interaction between its electromagnetic fields that sort of causes all of that to happen. Lastly, let's look at these two equations here. So if you look at E equals mc squared, very famous equation. What it says is that energy is equal to mass times speed of light constant in a vacuum squared. The idea is that mass and energy can be interconverted between each other, as you can see with the equal sign, and that even if you have a very, very small amount of mass, because the speed of light is such a large number and then squared, that can be converted to a very large amount of energy. Which again, we've already talked about that with the nuclear binding energy. And so, so that's called mass energy equivalence. Another idea that Einstein proposed is that energy and mass are sort of very similar. They're almost the same thing, in the sense that they're both derivatives of the same fundamental entity. I mean, we don't understand what that entity is, but they're interchangeable. They can be converted to one another. And that's kind of what happens in nuclear reactions, is that mass is being converted to energy. And since, again, a little bit of mass can have so much energy, so much nuclear binding energy putting together, it releases so much energy when you do that. So on this equation right here, so if you look at photons, you try to put photons, again, their masses and try to speed of light. Since they have no mass, you plug 0 into here, and you get 0 everything because you're multiplying by 0. So that doesn't make sense, which is why, in order for it to make sense, you have to realize that this equation right here is actually where E equals mc squared comes from. So this comes from this. This is a longer, bigger version, and this is kind of just like a specific scenario where you can rewrite this with. And so if you look at this equation and you take into account that photons have no mass, so what is P? P is if P is equal to 0, that means it has rest mass. Then this equation right here has to do with stuff that has rest mass. This, you can plug P into here, and mass is 0, and so this whole thing's gone. And then P can't be 0 because everything will be 0, which is why it can't be not moving. It can't be at rest. It has to always have momentum, which is why photons exist. I think that's it for this. Let's look at this. This is a little bit of review. What is an atom? It's kind of small. It's very small. It's mostly empty space. There's been experiments done with that. It maximizes for potential energy, like we talked before. The potential energy of the atomic nucleus the potential energy of when the atom, all the building blocks are put together, is less than the sum of the individual parts. We're going to talk about nuclear binding energy. Transition energy is the amount of energy needed to move an electron into a higher orbital. So we know what protons, neutrons, and electrons are, but what determines chemical properties of each element and compounds the element's form? So that's kind of like the next slide, which is math. So I'm not going to read this word for word, but it says medicine is basically biology, biology is chemistry, chemistry is physics, physics is math. Math is just math. It's just to say that science as a whole, and most of what happens in terms of materialism, all the physical interactions that things have with each other, all the chemical reactions that things have with each other, is due to math. And everything is represented, most everything can be represented with a mathematical equation, or probably multiple, like a set of them, and models and graphs and diagrams and all of this. So everything really, if you just look outside, you look at everything, you see how things are reacting to chemical reactions, and you look how things are falling or moving, which is physics. It really is just all of this. This is what you're looking at. Most everything can be described with math. And there's only a few things that doesn't account for it, such as consciousness, and consciousness doesn't make sense. We shouldn't be conscious. It doesn't fit into a materialistic understanding of the universe. And then additionally, intra and intermolecular forces also contribute to the unique properties each chemical compound has. So why does water this way? Why is wood this way? Why does glucose does this? Everything that moves and interacts with each other in ways we don't understand, well, we do understand, and we might not understand every single math equation that goes behind everything, but we do know that there is one, essentially. I can talk about that. So this is kind of just like a visual representation of what I mean by everything. The reason why chemical reactions are happening the way they do is because of the interaction between the sort of electromagnetic fields of the protons and the electrons, and being countered by the neutrons. It's all math. If you could look at this and you could quantize it, you could draw graphs for it, and this is kind of like a sort of like premiere of what that is. It's all math. Quantum mechanics. This is the last slide. So quantum mechanics doesn't have to do specifically with the electrons. It can do with a lot of things relating to just stuff on the small level. But one of the very popular things it does deal with is electrons. So a few things with electrons. Electrons are understood as having wave-like or wave-particle-like duality, or a wave-like particle duality, which means that in some scenarios when you measure it, it can act like a wave, and in the other scenarios it can act like a particle. It's kind of weird. This only happens with really, really small stuff. Another thing we have is the Heisenberg uncertainty principle, which says that you can't simultaneously know some electron's position as well as its momentum, or like how it's moving. And the more you know about one thing, the less you know about the other. And then here, the Pauli exclusion principle is that we have these four quantum numbers, to describe electrons within an atom, where they are, how they're moving, the cloud of probability in which they are moving. And the Pauli exclusion principle basically says that no two electrons in the same atom can have the same four quantum numbers. So each electron in an atom is, by conclusion, is doing something different. No two is completely identical in the way that it moves. I guess in the way it's made up, it's identical, but not in how it's moving. So the four quantum numbers, it's principal, angular momentum, I don't know why it says this, magnetic, and spin. So principal, let me zoom in. Principal is, quantum number, is basically the average distance of, okay, so we don't understand electrons as being in fixed orbitals, kind of like how the sun, how like planets orbiting the sun move in a fixed orbital. Instead, we understand it in terms of clouds of probability. So it can be here, or here. We don't know, you can't predict exactly, but when we do the math and we take a lot of data, we can find the sort of the probability that is going to be in this area is greater than in this area. So that's what we mean by clouds of probability. Another thing on the movement of electrons, as far as we know, movement of electrons is completely random. Again, we can predict somewhat, but the part that we can't predict is due to its randomness, and it's not because we can't, it's not because we're stupid or silly and we can't figure it out. It seems to be that it's more so because it really is just random. There's no possible measurement by which we can measure it. So that's the first one. Principle is how far it is away from the nucleus, and how much energy it has. Second is the shape of the orbital. So if it's like shaped like this, shaped like that. And again, and then magnetic has to do with the shape's orientation in space, and spin has to do with whether it's spinning this way or that way. And spin can only be in integers of plus 1/2 or minus 1/2. The idea of spin is similar to the idea of planets orbiting the sun, which is that while planets are orbiting the sun, they're also spinning at the same time. This is just to show that the periodic table is organized in a very specific way. It's not just random. And some part of that has to do with, as you can see here, with the quantum numbers. So it's not just random. And again, all of this, the reason why electrons are sort of configured in the way they are is because there's something about the configuration of each electron that is mathematically it works out mathematically. Again, they repel each other, and so they move in these ways and in such a way so as to stay as far away from each other while also still being attracted to the protons of the nuclei. And then the neutrons are oriented exactly where they are because protons repel each other. Protons repel protons, and so naturally they're going to want to get away from each other, but as you see, they're so tightly packed together, and the neutrons sort of help balance that out. And it's very specific, and yeah, I think that's it.